Millions of American homes stay warm and cozy thanks to a material that few people ever think about: Rockwool insulation. Rockwool, also called stone wool, is one of the most effective and sustainable insulation materials in the world. It's fire-resistant, water-repellent, sound-absorbing, and incredibly durable. And the best part? It's made almost entirely from natural stone, basalt, combined with recycled slag from steel mills. Today, we'll take you inside the supergiant Rockwool factory, where raw basalt is transformed into high-tech insulation, step by step. From quarries to furnaces, spinning machines to packaging lines, and even into homes across America, you'll see how this incredible product is born. But before we dive in, don't forget to like, subscribe, and hit the bell icon so you never miss another behind-the-scenes look at how the world's most essential materials are made. It all starts with basalt rock. Basalt is a dark, dense volcanic stone formed millions of years ago when lava cooled rapidly at the Earth's surface. It's abundant, incredibly strong, and naturally rich in minerals like silica, alumina, and iron oxide. In quarries across the US and around the world, enormous machines dig, drill, and blast basalt from the earth. Giant excavators scoop up boulders weighing several tons, which are then loaded into heavy-duty dump trucks. These trucks thunder down the quarry roads, carrying their black rock cargo to be crushed and sized. Once at the processing plant, the basalt is broken down into smaller chunks, about the size of a fist. Why? Because these chunks are easier to feed into the furnaces that will melt them. At this stage, it's almost impossible to imagine that these dark, jagged rocks will soon be transformed into something as light and woolly as insulation. But once inside the factory, fire and air will completely reshape their identity. Inside the supergiant Rockwool factory, the first jaw-dropping step is the melting process. Basalt rocks and slag are fed into gigantic cupola furnaces, massive, cylindrical ovens capable of reaching 500 degrees Celsius, 2,732 degrees Fahrenheit. Here, the rocks don't just heat up, they turn into a glowing, liquid lava. Flames roar, fans blast oxygen into the furnace, and the roar of the machinery makes it feel more like the inside of a volcano than a factory. This is no coincidence. Engineers are literally recreating volcanic conditions to melt rock back into magma. The molten lava collects at the bottom of the furnace, glowing orange and yellow. It's tapped continuously through a spout and flows like honey into the next stage of production. Workers in protective suits monitor every detail: temperature, viscosity, chemical balance, because even the slightest variation can change the quality of the insulation. Watching solid stone transform into liquid fire is breathtaking. In a matter of minutes, something that was once as unyielding as a mountain has become fluid, ready to be reshaped into one of the world's most versatile building materials. But the real magic happens next, when this lava meets air, speed, and a bit of human ingenuity. Once the molten basalt is ready, it's funneled onto high-speed spinning wheels or spinners. Imagine a cotton candy machine, but on a scale so massive it makes your head spin. As the lava hits the spinning wheels, it's thrown outward in thin streams. Cold air blasts across these streams, solidifying them instantly into fine fibers. In seconds, the lava is no longer liquid. It's transformed into strands of stone wool as thin as a human hair. Billions of these fibers float through the air, looking like a glowing storm of golden threads. Giant suction systems capture and guide them onto conveyor belts, where they form thick mats. But these mats are still loose and fragile. To strengthen them, a special binder is sprayed onto the fibers. This binder, often resin-based, holds the fibers together once they're cured. The mats are then layered, compressed, and passed through curing ovens. These ovens heat the mats to set the binder, locking the fibers into a solid, stable structure. Depending on how they're processed, the final product can be soft, fluffy bats or rigid boards capable of withstanding extreme pressure. What's incredible is how much the material has changed. Just hours ago, it was basalt rock, dense, heavy, and unyielding. Now it's light, elastic, and flexible, with millions of air pockets that trap heat and sound. This transformation, stone into wool, is the heart of the Rockwool process, and it's what makes the material so valuable for modern construction. Once cured, the Rockwool mats move on to precision cutting machines. Massive blades and lasers slice the insulation into specific shapes and sizes: bats, rolls, or boards. Each piece is measured to exact dimensions, ensuring it will fit perfectly between wall studs, ceiling joists, or industrial pipelines. But before anything leaves the factory, it undergoes strict quality control. Samples are tested for density, compressive strength, water resistance, and fire performance. Rockwool has to meet incredibly high standards. It's not just about comfort, but also about safety. In fact, one of Rockwool's most impressive features is its fire resistance. Because it's made from stone, it can withstand temperatures over 1,000 degrees Celsius, 1,008 degrees Fahrenheit, without melting or releasing toxic smoke. That makes it an essential barrier in buildings, giving people more time to escape during fires. After passing all inspections, the insulation is packaged, either wrapped in plastic for rolls and bats, or stacked on pallets for rigid boards. Forklifts load them onto trucks, ready to be shipped to construction sites across America and around the world. Rockwool is everywhere. In residential buildings, it keeps families warm in winter and cool in summer, while cutting down on energy bills. In offices and studios, it dampens sound, making spaces quieter and more comfortable. In industrial settings, it insulates pipes, furnaces, and equipment, protecting workers and saving energy. It's also eco-friendly. Up to 40% of the raw material can come from recycled slag, and the product itself can be recycled indefinitely. Plus, by improving building efficiency, Rockwool saves millions of tons of carbon emissions each year. If you enjoyed this deep dive into the supergiant Rockwool factory, don't forget to like this video, subscribe to our channel, and turn on notifications. Your support helps us bring you more behind-the-scenes documentaries about the industries, factories, and technologies that shape our world. Stay curious, and we'll see you in the next video. Leaf springs may look like simple curved strips of steel stacked together. But behind that simplicity lies an incredible engineering process. Every time you step into a truck, bus, or even a heavy-duty off-road vehicle, you are relying on a part you may never see. But without it, the ride would be rough, unstable, and unsafe. This hidden hero is the leaf spring, one of the oldest and most reliable suspension components in automotive history. From raw steel billets to heat-treated, precision-curved springs capable of carrying tons of weight, the journey is nothing short of mind-blowing. Today, we'll step inside a supergiant leaf spring factory, where millions of these suspension parts are produced each year for vehicles around the world. We'll uncover how steel is transformed, step by step, into the springs that keep our vehicles rolling safely and smoothly. Before we get started, don't forget to like, subscribe, and hit the bell icon so you won't miss any of our deep dives into the fascinating world of industrial production. The history of leaf springs goes back hundreds of years. They were used in horse-drawn carriages in the 18th century and became standard in early automobiles. Even today, despite advancements in technology, the leaf spring remains unmatched for certain heavy-duty applications. But how do you take raw steel and turn it into this iconic, powerful part? The answer lies in a carefully designed manufacturing process that combines metallurgy, heat treatment, and precision engineering. It all starts with alloy steel, a special kind of steel enriched with elements like silicon, manganese, and chromium. These alloys increase strength, toughness, and fatigue resistance, which are essential for springs that will flex thousands of times without breaking. The steel usually arrives at the factory in the form of long billets or flat bars, several meters in length. Each bar is carefully inspected for surface defects, cracks, or impurities. Quality control at this stage is vital, because any weakness in the material could result in spring failure later. Once approved, the steel bars are cut into precise lengths, depending on the size of the leaf spring being manufactured. For heavy trucks, a single spring can be up to 1.5 meters long, while smaller vehicles use shorter sizes. From here, the transformation begins. Steel is incredibly strong at room temperature, so to shape it, factories use furnaces that heat bars to over 1,000 degrees Celsius, 1,008 degrees Fahrenheit. Inside the furnace, the steel glows a bright orange red, reaching the perfect temperature for forging. Once heated, the steel bars are moved to powerful forging presses and rolling mills. These machines bend and flatten the steel into the familiar curved profile of a leaf spring. For multi-leaf springs, thinner strips are produced and stacked later in the process. The curvature, or camber, is critical. Too much curve, and the spring becomes stiff. Too little, and it can't support enough weight. Precision dies and hydraulic presses ensure every piece has the exact shape needed for its intended vehicle. For springs with eyes at the ends, the circular loops used to attach the spring to the chassis, hot forging machines roll the edges into perfect rings. These eyes must be incredibly strong, since they bear much of the stress during driving. By the end of this stage, the steel bars have been transformed into recognizable leaf spring shapes, but they're still far from ready. Without further treatment, they would bend permanently or snap under pressure. One of the most fascinating steps in the process is heat treatment. The forged springs are reheated to high temperatures and then rapidly cooled in oil or water baths, a process called quenching. This sudden cooling hardens the steel, giving it the strength to withstand enormous loads. However, quenched steel is also brittle. To restore flexibility, the springs undergo tempering. They are reheated to a lower temperature and held there for several hours. This balances hardness and toughness, ensuring the springs can flex repeatedly without cracking. Some factories also use shot peening, blasting the surface of the spring with tiny steel balls. This creates compressive stress on the surface, dramatically increasing fatigue resistance. It's like giving the spring a protective armor, extending its lifespan by years. At the end of this stage, each spring is incredibly strong, flexible, and ready to take on the brutal forces of the road. While some vehicles use a single leaf spring, most heavy-duty trucks rely on multi-leaf springs. These are stacks of steel strips, each slightly shorter than the one below it, forming a tapered profile. The leaves are carefully assembled in layers, aligned perfectly, and clamped together with a central bolt. Steel clips are added along the sides to hold the stack in place while still allowing the leaves to flex individually. This design spreads loads evenly, reduces stress on any single leaf, and provides both strength and flexibility. It's a simple yet brilliant engineering solution that has stood the test of time. Before leaving the factory, leaf springs undergo several finishing processes. First, they are ground and polished, removing sharp edges or surface imperfections. Next, protective coatings are applied. Factories often use electrostatic painting or powder coating to protect against rust and corrosion. Then comes the most important step: testing. Every batch of leaf springs is subjected to rigorous quality checks. Machines flex the springs thousands of times under simulated loads, measuring how well they maintain their shape and strength. Only those that pass these tests are approved for shipment. Today, millions of leaf springs are produced every year, powering vehicles all over the world. From American trucks hauling freight across highways, to buses carrying passengers in India, to mining equipment in Africa, leaf springs are everywhere. Despite being centuries old in design, they remain one of the most dependable suspension systems. Their simplicity, strength, and low cost make them indispensable in industries where durability matters more than luxury. And it all comes back to the mass production process, a blend of fire, steel, and engineering precision that transforms raw alloy into one of the most vital automotive parts on Earth. It's a reminder that even the simplest-looking parts in a vehicle often have the most fascinating stories. Stories of heat, pressure, engineering, and innovation. If you enjoyed this behind-the-scenes look at automotive manufacturing, don't forget to like, subscribe, and hit the notification bell. We have many more stories coming about the amazing machines and factories that keep our modern world moving. Until then, drive safe and stay curious. In America alone, tens of millions of locks are produced every single year. How exactly is a lock made? What goes into crafting something that must be strong enough to stop thieves, precise enough to work flawlessly thousands of times, and durable enough to withstand years of use? Today, we're going to take you deep inside the world of lock manufacturing. From raw metal to finely crafted mechanisms, we'll see step by step how locks come to life, and the process might surprise you. Because behind every lock is a fascinating combination of metallurgy, machining, precision engineering, and even art. Before we jump in, don't forget to like, subscribe, and hit that notification bell so you never miss more eye-opening documentaries about how everyday things are made. Now let's unlock the story. Locks have been protecting people for over 4,000 years. The very first locks date back to ancient Egypt and Mesopotamia. These were simple wooden mechanisms, often with pins that could be lifted by a specially shaped key. Although primitive by today's standards, the idea was revolutionary, a barrier that could only be opened by someone who had the right tool. Fast forward to the Roman Empire, and locks evolved into more sophisticated metal devices. Romans were some of the first to use metal wards and keys, sometimes even wearing small keys as rings on their fingers for convenience. In the United States, companies like Schlage, Kwikset, Yale, and Master Lock transformed lock manufacturing into a large-scale industry, supplying everything from padlocks for soldiers in World War II to deadbolts for suburban homes in the 20th century. Understanding this history is important because modern lock production combines centuries of knowledge with cutting-edge technology. And with that background, let's step inside a factory and see exactly how a modern lock is made. At the heart of every lock is metal. Most locks are made from brass, steel, or zinc alloys. Brass is especially common because it's strong, resistant to corrosion, and relatively easy to machine. The process begins with large shipments of raw metal arriving at the factory in the form of bars, rods, and sheets. These materials will eventually be shaped into the body of the lock, the shackle in padlocks, and the intricate parts inside the locking mechanism. Before anything is cut, the metals are tested. Factories use spectrometers to confirm chemical composition, ensuring that the brass or steel meets exact standards. A weak alloy could mean a lock that fails too easily, something manufacturers cannot risk.